Each transformer coil begins with a solid hot-rolled copper rod delivered to the production floor.
The rod tip is mechanically cleaned and shaped to allow smooth entry into the reduction die. Graphite lubrication reduces friction between the copper rod and the drawing die during compression.
The tungsten carbide die compresses the copper rod, reducing diameter under controlled mechanical tension.
After the first compression stage, the copper becomes smoother and structurally denser.
Sequential die stages progressively decrease the rod diameter while maintaining concentric alignment. Controlled speed adjustments ensure uniform reduction without internal structural defects.
The original solid copper rod has now entered the intermediate wire stage and will undergo further reduction and heat treatment.
Each precision die compresses the copper wire further, refining diameter and improving surface uniformity.
The fine copper wire enters a continuous annealing furnace to relieve internal stress caused by mechanical reduction. Annealing restores ductility, allowing the copper wire to bend without structural cracking. The softened annealed copper wire is prepared for enamel insulation coating. The applied enamel layer is cured under controlled heat to form a solid electrical insulation barrier. Multiple insulation layers are applied and cured to ensure electrical resistance and mechanical durability. Laser measurement systems verify insulation thickness and diameter consistency in real time. The insulated copper wire is guided into a precision coil winding machine for transformer bobbin winding. Controlled spindle rotation and lateral wire guiding ensure uniform winding distribution. Interlayer insulation prevents electrical short circuits between adjacent winding layers. Automated cutting and anchoring complete the precision winding sequence. A heavy laminated steel core frame is prepared to receive high-capacity copper windings. Large transformer coils require uniform tension control to prevent mechanical deformation. The winding sequence concludes with extended copper leads for electrical termination.
The core looks good and the winding thickness is spot on.
Agreed.
I've logged the inspection. We can move it to the reinforcement station.
The completed copper winding block is cleaned before applying additional structural insulation layers. Rigid insulation panels reinforce the winding structure and protect the copper layers from mechanical stress.
Hydraulic compression stabilizes the copper winding layers before resin impregnation.
All right, tighten that one down. Sounds good. That should hold the core frame steady.
Dimensional inspection ensures structural alignment before vacuum impregnation.
The reinforced transformer coil assembly is positioned inside a sealed vacuum impregnation chamber. Vacuum pressure removes trapped air from the copper winding structure and insulation layers. Under vacuum conditions, the insulating resin penetrates every cavity within the winding structure. Excess resin is drained while the internal winding structure remains fully impregnated.
Okay, easy now. Clear on the left side. Coming down slowly. Watch your hands.
The resin-saturated transformer coil is transferred into a controlled thermal curing oven.
Elevated temperature initiates epoxy resin polymerization, solidifying the internal winding structure.
Controlled cooling prevents thermal stress and preserves winding alignment.
The cured epoxy resin bonds copper windings and insulation into a rigid, vibration-resistant structure.
The hardened transformer coil is prepared for integration with the laminated magnetic core.
Copper winding leads are routed and prepared for external electrical connection.
Make sure it's flush against the core.
Looks good. The spacing is exactly 5 millimeters here too.
Mechanical alignment ensures stable magnetic flux distribution during transformer operation. The assembled core and coil structure is positioned inside the transformer tank enclosure.
The magnetic core assembly is bolted securely to prevent internal movement during operation.
External radiator panels allow transformer oil to circulate and dissipate operational heat. Air and moisture are removed from the sealed tank before insulating oil is introduced.
Filtered transformer insulating oil is transferred from a sealed storage tank into the transformer enclosure.
Insulating oil displaces remaining air pockets and surrounds all internal components for electrical insulation.
Low-pressure air testing verifies structural sealing of the transformer tank.
Stable pressure readings confirm that the tank structure is airtight and leak-free.
The oil-filled transformer is transferred to the electrical testing area for performance evaluation.
Insulation resistance testing confirms that winding insulation and oil integrity meet safety standards.
The dielectric withstand test verifies the transformer's ability to handle rated operating voltage.
Acoustic and vibration testing ensures stable magnetic core performance under load.
Before shipment, the transformer tank surface is cleaned and inspected for cosmetic defects.
Final coating inspection ensures corrosion protection and uniform surface finish.
Protective terminal covers are installed to safeguard electrical connection points during transport.
The transformer unit is wrapped to protect against moisture, dust, and mechanical impact during shipping.